Saturday Morning Physics is sponsored by the University of Michigan Department of Physics and by gifts from friends of the program. Local broadcast is made possible by Pfizer Incorporated.
There are some things in what we talked about last time that were really left out, very important things. Like, if we want to say that the Big Bang really happened like this, we should have a theory for this expansion, including a picture of how it will expand in the future. This theory was really lacking in the descriptive model that we talked about last time. There are also a couple of problems or a couple of things that happen in the universe that we need to be able to explain if this is going to be a successful scientific theory. And two of those are the homogeneity of the early universe, the fact that the universe looked so similar everywhere in the early universe. We have to be able to explain that, and we'll talk about that. And then we have to explain how it went from this very homogeneous early universe to the very inhomogeneous universe that we see today. This talk, because it talks about extensions of the simplest kind of picture of the Big Bang model, will be somewhat more technical than the talk we gave last time. There are some very important details here that I want to try and get across, and so I'll have to ask you to bear with me to try and understand some of these more technical points. So last time we talked about 3 facts about the universe that we now have well established, and those facts are that the universe today is expanding. This can be measured very well, and we'll talk about it a little bit more in a second. That the universe is filled with a uniform glow of perfectly thermal 2.7 degree Kelvin radiation. This is the heat radiation that is still streaming toward us from regions of the universe that released it right after the Big Bang. We see that thermal radiation, which was predicted in advance, with exactly the form that it should have had, and it's one of the great confirmations of the basic picture of the Big Bang. The third very important fact is that the matter that constitutes the universe, the kinds of atoms that make up the universe, are mostly hydrogen and helium. And that dominance of light elements is something that needs to be explained by any theory for the origin of the universe, and this Big Bang theory has a natural explanation for it. In fact, all 3 of these facts are understandable within this Big Bang model. This idea of expansion is intrinsic to the model. It's the essence of it. We see the universe expanding now. It used to be smaller. That background radiation, which is observed all over the universe, was perfectly predicted, and it was expected to be this kind of perfect thermal radiation. It turned out to be just that kind of perfect thermal radiation. And finally, the dominance of these light elements, the fact that the universe is so much made of hydrogen and helium, is perfectly explained by this kind of origin model. So let me just recap those 3 points a little bit. Before I do, I want to tell people who perhaps weren't here last time a crucial fact about understanding cosmology. And that is that light travels at a finite speed. And since light travels at a finite speed, when we look at a distant object, we don't see it now, at this instant. We see it as it was at some time in the past. If that object is very distant from us, then it takes the light a long time to reach us. And so when we look at a distant object, we see it in the distant past. If the object is more nearby, then when we look out, we see it in the more recent past. And finally, if an object is close to us, as you are to me, I see you in the recent past. So I see all of you a few nanoseconds ago. And if you were very quick, you could get up and leave the room, and I wouldn't know for a few nanoseconds. So the important thing about this for cosmology, though, is that when we look out in the universe, when we look far away, we can see what the universe used to look like. We can see its past laid out before us. And this is very like the way we do geology on the Earth. The history of the Earth is lying there in layers, and the history of the universe is spread out around us in spheres, so that we can look out and see that history. This uniform expansion is an essential piece of the Big Bang theory, and it comes from the observation that when we look out at objects in the universe, we find that every object at any reasonable distance from us is moving away from us. And in such an expanding universe like this, every object moves away from everything else. You start out with a universe where there are a few things close together, and then you expand every part of that universe. You make everything about it bigger, and things all move apart from one another. It's not that any one object sits in the center and things are moving away from it. Every object moves away from every other object in this kind of expanding universe picture. This expanding universe that we see in our own universe is a universal thing. There are no things that violate this rule. Every object which is very distant from us is also moving away from us very fast. It's receding from us. There are no exceptions to that. And that's a picture that can only be accommodated in this kind of expanding universe model. Now, when we talked about how we can tell that the universe is expanding, we said that we measure the velocity that galaxies are moving away from us by looking at their redshift. And that's actually not really correct. It's not that we're measuring the velocity of a galaxy. What we're doing when we measure the redshift, how the light from a galaxy has been stretched out, is we're measuring how much the universe has expanded since the time that the light left that galaxy. So it leaves that galaxy at some point in the past, maybe millions of years ago. It's traveling across the universe, and as it travels across the universe is expanding underneath it. So the light stretches out with that expanding space. So rather than measuring a velocity where we can, at this instant, measure the velocity of that very distant galaxy, instead what we do is we let that light slowly travel across the universe towards us, and as it does so, it gets stretched out and measures for us how much the universe has expanded since the time that it left. All right? So when we make a figure like Hubble made to show this expansion versus distance, he would have measured the distance out to a galaxy and its recession velocity. But now we have a better way of thinking about that, a more appropriate way of thinking about that, is to say that this distance, since light travels at a finite speed, that distance tells us a time. And when we look out at more and more distant things, we're looking at things farther and farther back in time. And so this is a measure of how far back in time we're looking. And on this axis, rather than that being a measurement of velocity, what it really is a measurement of how much the universe has expanded since that time. And so if we look out at objects which have light that left them 1.6 billion years ago, what we will see is that that light has since that time stretched by 10% of its original length. When we look way out, when we look out at the most distant things we can see, what we see is the universe at the earliest time that we can see it. And at that very early time, the universe was hot and dense and uniform because it was much smaller than it is now. And so light has been propagating from that very hot, dense early time toward us for the whole age of the universe, and it's just reaching us now. So these are the most distant things that we can see, and they have a distribution of light, a mixture of colors, which is exactly the mixture that is predicted for this kind of thermal radiation. And that, too, is a very important confirmation of this Big Bang picture. Finally, the third piece of this Big Bang picture that we talked about last time had to do with the construction of the elements that make up the universe. When you take matter and you put it in a very hot and dense state, it's possible to make the light nuclei that make up atoms, it's possible to make them burn, to combine with one another and release energy. In very much the same way that if you take a piece of paper and you heat it up to the appropriate temperature, it's possible to make it burn and release energy. So this nuclear energy can be released if you put nuclei together in a dense and hot enough environment. Those light nuclei will combine together to form heavier and heavier nuclei and release energy. If you do this in a stable nuclear furnace and you let it keep going, you let it burn all the way through, then you'll have something very like what happens in a star. And if you let the elements continue to cook inside your oven, what they will do is they will burn all the way up to iron. And so if the elements in our universe were all made in stable furnaces like this, then the universe would be dominated by heavier elements like iron. But instead, the universe is dominated by light elements like hydrogen and helium. And that comes about because instead of letting the elements cook for a long time, they cook only very briefly during the very brief, hot, early period of the universe. They don't have long enough to cook all the way up to iron. Instead, it's something much more like an unstable nuclear furnace. And there's an example of an unstable nuclear furnace from March 1st, 1954, an atmospheric test of a hydrogen bomb. This fuses lots of hydrogen into helium, but it doesn't make many heavier elements because it doesn't last long enough to do that. All right, so this gave us, by the end of our talk last time, these three pillars of the hot Big Bang theory, and we selected three pillars from Angel Hall to describe them. The first one was cosmic expansion. And it was because of cosmic expansion that people started to think really deeply and seriously about this issue. The discovery of cosmic expansion was the first big clue that we might have had an early, hot, dense universe. The second part was this background radiation, which was predicted and then observed with just the properties that were predicted, a very important confirmation of the basic picture. And finally, there's the light element abundances, the fact that the elements that make up our world were cooked in a temporary furnace rather than a permanent furnace. So those are the three pillars of the hot Big Bang theory. And that's a quick summary of the things we talked about last time. Let me say a few things about some common Big Bang misconceptions. People will sometimes say the universe was just a tiny speck before the Big Bang, and then it grew and became really big. This is a misconception because the universe wasn't just a tiny speck when it began. All of the stuff we see now was much closer together, but as far as we know, the universe at that time was perfectly infinite. We have no reason to believe that it wasn't just as infinite then as it might be today. It's just that the part we're in, the part we can see, was everything was much closer together. It was much smaller then. It's not that it was one speck inside empty space. So that leads to the second question, what are we expanding into? If you imagine a speck, it must be sitting in something, and then it expands into it. But if you imagine a universe which is infinite and everything is just close together, then you don't have that issue. It's not that it's expanding into something, it's just getting bigger. There is this question about how far galaxies can expand before there's nowhere left to go. All right? And this is really the same kind of question. If you're expanding into something, well, maybe it has an edge, and you'll fall off the end. People have worried about falling off the ends of things for a long time. But in an expanding universe, it's not a real concern. Then there's this question that Woody Allen posed. Is Brooklyn expanding? And the answer to that is no, it's not. It's not obvious that this would be the case, really, from the description that we usually give of the Big Bang. But although the space is expanding, objects like you and me in this table are actually being held together by forces, and those forces continue to act. They don't just let the object expand away. They keep the object the same size that it is. So Brooklyn and the Earth and you and I are not expanding due to cosmic expansion. Then there's a question about what's the center of the universe, because again, if you have this picture of an explosion going outward, there must be a place it's coming from. That's the whole point of universal expansion, is that when you have expansion, every point moves away from every other. You can sit on any galaxy that you want, and you will see every galaxy moving away from you. It's a universal kind of expansion. And it avoids this problem that otherwise, when we see things moving away from us, we would have to have a center, and we would have to be at it. People often ask questions like, how much does the universe expand in one day? So I worked it out. 1 meter grows by 2 times 10 to the minus 13 meters every day. So if you went out into interstellar space and you could lay down 2 things that didn't interact with one another and wait a day, they would be 2 times 10 to the minus 13 meters farther apart the next day. Not very much. And then there's this very interesting question. How do we know how long ago the Big Bang happened? And there's nothing in what I told you last week that can answer that question. All we said last week was, we see the universe expanding. Well, it must have been smaller before. And if it was smaller, it must have been dense. And if it was dense, it must have been hot. So there would have been Big Bang radiation, and there would have been light element production. But it was all like this, very hand-wavy, right? Because there was no theory, no model underlying what we talked about last time. Just a kind of a picture, a story. So if we want to be able to answer very important questions like, how do we know how long ago did the Big Bang happen, we need a theory, a quantitative theory for understanding this. Fortunately, there is such a theory. And in fact, remarkably, the theory was created before the expansion was discovered. What we talked about so far is just kind of a conceptual framework, and in order to turn this into a scientific theory or a scientific explanation, we need a full theoretical framework which says, how does the expansion happen, and gives us the dynamics, the theory to predict precisely how that expansion should happen. This underlying theory was worked out, as I said, before the expansion was discovered by none other than Albert Einstein. So here's a nice picture of him with lots of other famous scientists, and if you zoom in, you can see there's Einstein, and there's Hubble. All right. Einstein worked out this theory of expansion. And again, it's not a theory of expansion into something, but a theory of expansion of the space itself. A lot of his life's work was involved with this theory of relativity, with understanding space and time and how they couple together, and the surprising ways that they're different from people's simple intuition. The first theory that he wrote down in 1905, 100 years ago, in a very famous paper called The Electrodynamics of Moving Bodies, what he did is he described how the world would be seen by different observers, you and I, for example, if we were moving at constant speeds relative to one another. And he discovered some astounding things. He discovered that clocks that I carry and that you carry would not work in synchrony anymore. They actually would run at different rates. Time was not absolute, but was relative. He discovered that lengths likewise had this kind of contraction, and he wrote down the most famous equation in physics, E equals mc squared, saying that mass, this m in this equation, and energy are really the same thing. They can be converted one to the other back and forth, and that the conversion factor between the two is the speed of light squared. The speed of light is a big number. So when you square it and you multiply it by a mass, you get a lot of energy. So it told us that there was a lot of energy available there in the form of mass energy. Now, Einstein knew from the beginning that this theory was partial. It was the first step. And it was because it had this very strict restriction that those observers should be traveling at constant relative speed to one another. When we look out at the world, we see lots of things changing their speeds all the time. There are accelerations. And he needed a theory to describe space-time as it's seen by different observers who accelerate relative to one another. He knew this was the problem, and he set to work on it. It took him a long time to come to the conclusion, in part because the mathematics was very new to Einstein, although there were mathematicians who had studied this kind of mathematics before. It was very new to Einstein, and the ideas were very slippery, so it took him quite a while in order to understand it. What he did in the end to create this theory was to explain gravity in terms of geometry. In order to create a theory of space-time which would be valid for all observers, he had to explain gravity. He had to explain how gravity makes things seem to accelerate. And what he said is that in this theory of general relativity, gravity is something that comes about from the space-time itself. That the space-time in which an object moves is what tells an object how to move. So instead of saying there's a force of gravity that reaches out and grabs an object and pulls it in one direction or another, all that happens is the object looks at the space-time where it is and moves in a straight line in this curved space-time. Furthermore, he coupled the two things together so that the matter which is in the universe communicates with the space-time and tells the space-time how to curve, while the space-time tells the matter how to move. And we have a quick demonstration to try and show you that. What we have here is a space-time, otherwise known as a sheet of rubber, which we can make curve. When that space-time is flat, what will happen if I send an object across it is it will travel in a straight line. That's because the space-time is flat. An object moving through a flat space-time travels in a straight line. What Einstein said is that if I put a mass in the middle of that space-time, it will curve that space-time. The matter will tell the space-time how to curve. So when I set it down, that space-time becomes curved. You can't really see it when you look up on the screen, and you can't really see it when you look out in the world. The way you can see it is to put an object in there and see how that object will move. So if I put this object into the curved space-time, what it does is travel in a curved path. It's traveling in the shortest possible distance, the shortest possible path it can take in this curved space-time, but nevertheless it goes in a curve because the shortest distance between 2 points on a curved object is not a straight line. It's a curve. All right? The important point is that the space-time, which is the thing we're interested in, we want to know how space-time is going to evolve. That space-time is coupled together with the matter that's in the space-time. The matter is telling the space-time what to do. And then the space-time tells the matter how to move within that space-time. Okay? There's one arcane-looking equation which describes all this. And it basically says that you can write things down on one side of the equation that have to do with the nature of the space-time, how big it is, how curved it is. And then you can write things down on the other side of the equation that have to do with how much energy and matter there is in the universe. That's what's on the other side of this equation. The energy and the matter in the universe tell the space-time how to change. These two things are connected to one another. In order to describe it fully, he had to be able to write this in the context of non-Euclidean geometry, and that was one of the things he kind of wrestled with until he found mathematicians who already knew how to do it. But the important essence of what it says is that the contents of the universe, how much matter and energy there is in the universe, determines what happens in the universe. So if the space-time is going to change, if it's going to expand or contract, accelerate or slow down, that's going to happen because of the contents of the universe, because of what's in it. Now, this is not that shocking a thing. What else could change the way the universe evolves other than what's in it? There really isn't anything else that's likely to do that. So the energy and matter that's in the universe tells the space-time how to evolve. Now, there's a very important point I have to make here, which is that in physics theories describe dynamics. They tell us how things will change if we start them out in a certain way. So Newton's laws of mechanics tell me that if I throw a football at a certain angle and a certain velocity, it will travel a certain distance before it reaches the ground again. It can't tell me where that football will be thrown from or how fast I will throw it. Those are what you would call initial conditions. Physics governs what can happen after you get things started. It doesn't tell you how things got started. And in this same sense, this theory of general relativity does not specify how the universe started. So although it will give us a theory for explaining the expansion from the beginning up to now, it won't tell us why the universe started out the way it did. It won't tell us why there's a certain amount of matter in the universe. This theory of general relativity will just describe what will happen if I start out a universe, I have a Big Bang, what happens after that? It tells us how it evolves and how it changes. It's a very rich theory that talks about how space is curved around all different masses that might exist, and there's lots of wonderful science in that. But on a global scale, when we talk about what's going to happen in the future of the universe, this theory is really remarkably simple. The total amount of matter and energy in the universe is all we really need to know how the expansion of the universe will evolve. The contents of the universe, how much there is in it, decides between the continued expansion of the universe, an eventual recollapse of the universe, or a coasting to a stop at infinite time. Now, when Einstein first wrote this theory down in 1919, he believed the universe was static. He looked at the equations and they said, no, it's not static. The space-time is going to change. So he thought there might be something wrong with this theory. And he put into the theory a constant, something called the cosmological constant, to make it stable. All right, and he wrote it down, published it. A few years later, Edwin Hubble discovered that the universe was expanding. And Einstein realized he'd gotten it wrong, that he should have trusted the equations that he derived and believed that the universe was not stable, that it had to be evolving. The equations told him that, but he backed away from it and didn't stand by that idea. Of course, very quickly after Hubble's discovery, it was realized that this expansion that he was seeing, this rapid motion of things that are distant from us, moving away from us, that discovery meant that the universe was evolving. Einstein and Einstein's theory were quickly adopted to explain how that was happening and to give us a prediction for how the universe should change as a function of time, how much it should be expanding, how the rate should change, and everything else. So this theory of general relativity is the theory we use to predict how the universe should look, given how it looks at any particular instant, how it will evolve. So it predicts many relationships among things that we can observe. Things like how much has the universe expanded as a function of time. It makes predictions about just what that expansion should be as a function of time. So if we go out and measure it, we can check them. Remember, before we had general relativity, we didn't have a theory. We couldn't really predict these things. You could wave your hands and say maybe. But this is a real theory that can really predict them. It could predict things like angular diameter distances versus expansion. So if you look out at an object and you know how big it really is, if it's near you, the angle out to it is big. And if it's far away, the angle out to it is small. And in our normal flat universe, there's a simple relationship between those things. In an expanding universe, it's more complicated. And Einstein's theory allows us to predict exactly what that is. And furthermore, it allows us to answer that question that was asked. How do we know how long ago the Big Bang happened? Here's a theory that lets us calculate how long ago the Big Bang happened. I want to remind you that in order to use this theory to predict things, we have to know what the contents of the universe are, because all it says is that if you know the contents, you can predict the evolution of the universe. At the time when the theory was written down and when Hubble first discovered the expansion, we had no idea how much matter and energy there was in the universe. Early calculations were made that were wrong by enormous factors. So a lot of the 70 years between the time that Hubble made his discovery and today has been taken up with making measurements to understand the contents of the universe in ever-increasing detail. As we do that, our theory allows us to make predictions with ever-increasing levels of detail. All right? We can understand better only once we measure what these contents are. Now, the basic parameter, the most important parameter in this cosmology, is just the total amount of matter that's in the universe. And we write that total density with this symbol omega. All right? We're going to see that symbol omega coming up. It represents the total density in the universe. That's all it's about. What general relativity predicts is that there is, for the universe seen to be expanding the way it is today, there is a critical density for that universe. All right? That critical density will determine the way the universe expands. The relationship of the real density to this critical density determines how the universe will continue to expand in the future, whether it will stop expanding and collapse again, or whether it will continue to expand forever. If the real density is too high, then gravity will slow things down. That will cause more curvature, and it will stop the expansion and cause the universe to recollapse. If instead the total amount of matter in the universe is too low, then gravity can't stop the expansion, and the density will gradually fall to zero as the universe just diffuses away. Now, the equation that describes this critical density is strikingly simple. All right? It's an equation written up here in the corner. It says that that critical density is governed by only two numbers. One of them is the expansion rate measured at any particular time. So if we measure what Hubble measured, how fast are things moving away from us as a function of distance, then we get this number. All right? The other number that comes into this critical density is the strength of gravity, what's called Newton's constant. Because after all, it's gravity that's trying to pull things back, that's trying to stop things. If gravity were stronger, you wouldn't need as much density to stop this expansion. If gravity is weak, you need more. So that's how this equation works. This equation is trivially simple to calculate. You can think about it in the following way. If you imagine that you take an object and you throw it upward, it starts out with some velocity. That's like an expansion. It's moving away from you. It has some energy moving away from you. Gravity pulls back on it while that's happening. There is a critical velocity that it can have so that it will escape away from you forever. If it has less than that, it's going to fall back inward. This calculation is done in very much that same way. Here's a picture of how this general relativity theory predicts the scale of the universe will change. So the scale of the universe is a measure of how big the distances between things are as a function of time in the universe. All right? And it has right here the time we're at right now. So this part of the diagram is very well determined. We know how fast the universe is expanding right now. What we'd like to know is what did it do in the past and what did it do in the future. This scale factor shows the size of things relative to now. So now things have a size of 1. In the past, they were half as big or a tenth as big. And it shows that as a function of time measured in units of the age of the universe. So what we think is the real age of the universe is back here. These are other possible ages of the universe for different models. Okay? So when we look down here, what we see are possible beginnings of the universe. And in every one of those, you see that the universe starts out and that the rate at which the expansion is happening, the rate at which it's getting bigger, is big in the beginning. And it gradually slows down. All right? So you see that all of these slow down a little bit in the beginning. This theory can predict what it should have been doing in the past like this, all the way back to the beginning. It can also predict what it is doing in the possible future. And which of these possible futures the universe will have is governed by what's in the universe, by the contents of the universe. So we can learn about those contents by looking backward and seeing how the universe expanded in the past. Then we can apply that to understanding what the universe will do in the future by running these equations forward. There are two big problems that this theory has to address, or that any picture of the Big Bang has to address. And the first of those is what's called the flatness problem. It says that if the density of the universe is below the critical density, then very quickly the universe will expand to enormous size, and the density will fall off and be very, very different from the critical density. Because it's expanding, it's getting less and less dense. On the other hand, if the density is too large, then very early in the universe, it will recollapse. So in order to have a universe that lasts as long as ours, you have to start out with a density that's very close to the critical density. Right? You have to start out with just the right thing. And if you don't, the universe won't last long enough for us to see it, or it won't be dense enough for structures like the ones we live in to form. This is called the Flatness Problem. And it's illustrated by this figure from Ned Wright's webpage. Ned Wright is a professor at UCLA who has a very beautiful page on cosmology. What it shows is what would happen to the universe if at 1 nanosecond after the Big Bang you change the density. Okay, so there's 3 different densities shown here. One of them is this number, 447, 225, 917, 218, 507, okay? A lot of numbers. In the last digit here, you see there's a 7 grams per square centimeter, okay? This is the heavy one. Too much stuff in the universe. It recollapses, all right? This is the light one. It's 1 gram per cubic centimeter less than the critical density, and it expands very rapidly. And only if you have just the right density do you stay on this line that lives a long time. So it's exquisitely sensitive to that early condition. This is the flatness problem. There's a second big problem, which may be related to the flatness problem. And that's the fact that the universe is so homogeneous. We talked about this last time. When we look out at that microwave background radiation, we see the same temperature everywhere on the sky to a remarkable degree of accuracy, to about 1 part or a few parts in 100,000. It's really very similar in different places on the sky. Imagine that we start at some moment in the universe when there are a couple of little regions here that have each been cooking along since the beginning of the expansion. Each little region has come to be the same temperature, right? Because they've kind of equilibrated. The temperatures spread around until those little regions are the same temperature. This little circle that I've drawn contains everything in the universe that we see today. And as I said before, as far as we know, that continues beyond there as far as we can imagine, perhaps infinitely. But our little part of the universe is this piece in here. So what happens after the Big Bang, after this moment early in the Big Bang? What happens is that the universe expands. And when it expands, it cools. As we said last time, when it reaches a certain temperature, the light can start to propagate freely through it. It won't be absorbed anymore. It just goes freely. And so light that was emitted from our 4 little blobs on the corners of this circle starts heading in toward us. Now, it doesn't get to us right away, because not only are those places far away, but they're being carried still farther away by the expansion. So as time goes on, the expansion carries it farther away, and the light's still struggling to get in toward us. During this early expansion, the expansion slows due to gravity. The light begins to catch up, and eventually, the light reaches us today. Okay? So our 4 little blobs released light back at the time of the Big Bang, and that light has been traveling toward us all that time, and it finally got to us just today. So what's the problem with this? Light from each of these 4 points, from here and from here, for example, has just had time to reach us. It hasn't had time to reach the other side. So how could these 2 sides know what temperature they're supposed to have? What did they do? Did they send a Federal Express package across to say what it was? There's no way that they can have communicated with one another within this model. There's no way they can have adjusted to have the same temperature. So that's a big problem for this standard picture. How could they have precisely the same temperature? This is what's called the horizon problem, because we see it out at the edges of our universe, and it refers to that horizon, that most distant thing that we can see. Now, there is an idea for trying to explain this, and this idea is an extension of the simple Big Bang. The idea is this, that imagine that the universe, everything we see now, instead of being just really small before the Big Bang, was actually much smaller than that. It was really tiny. It was so tiny that that tiny region, which now encompasses everything we see, was at thermal equilibrium. It could all come to the same temperature. Now, you can't just make it expand according to the simple rules of general relativity governed by the matter we see in the universe today. If that was the case, we'd have the horizon problem. It has to do something more interesting than that. Perhaps that tiny little small region, which had enough time to come to be the same temperature, increased in size enormously, very quickly. Okay? Increased in size so that now everything we see was contained within one little tiny thing that came to equilibrium beforehand. It's kind of a crazy idea. It's called the theory of cosmic inflation, and it actually has a lot of interesting different motivations. And as we'll see, it has some real evidence for it now, very strong evidence. This theory was first written down by an MIT professor named Alan Guth when he was younger. Here's a picture of him here at the University of Michigan a couple years ago, showing us just how much the universe expanded during inflation. And you can imagine this poor guy has to do this all the time. So the idea of this inflation is that there was a very rapid, accelerating expansion for a brief period right after the Big Bang. All right? What this does is it takes a little tiny spot and inflates it to be something big, and then the universe continues from there. All right? So what you have to have is there's some initial expansion, which looks like the one that we talked about. It's getting bigger fast, and it's slowing down a little bit. And then something happens, and there's an inflationary epoch, a period of irrational exuberance in which the universe expands in size exponentially. Okay? So you see the rate at which the universe is getting bigger is increasing. The rate is increasing during this accelerated expansion. And then that inflationary epoch stops, and the universe continues on in the manner that we described already. So what it buys you is it lets you make the whole universe, everything we can see now, out of something really, really tiny. So that really, really tiny thing had the time in order to do this. Now, as I said, there are a lot of different motivations for this inflationary theory. A lot of different reasons why fundamental physicists like the idea of inflation. In the 1980s and 1990s, most experimental physicists like myself thought that was a completely silly reason to believe in something, because it had nice theoretical underpinnings. Okay? There has to be evidence for a thing like this. You can't just make up a story, yes, the universe expanded really fast in the beginning. That's not good enough. There has to be real evidence. And that's what's happened in just the last few years. There's come to be evidence. So to explain that evidence, I have to tell you a little bit about what it is that inflation does. First of all, it solves this flatness problem because it makes the universe so big. And you can think about that in the following way. If we turn on this expanding universe, it starts out small, and the curvature of the universe is big. It's really curved, right? You would see that. But once it gets big, once it gets a lot bigger, every little point on this universe, every little part of it, every little part of this universe starts to look more and more flat. All right? If you expand it enough, then any part that you happen to be in would be very flat, because it's gotten so big. All right? What that means is it solves the flatness problem, but it does something further. It says the universe must be very flat. The density must be the critical density. All right? It's a very firm prediction. Without it, you really can't have this kind of inflationary picture. It solves the horizon problem because everything came from one little place, and it solves this flatness problem as well, because it pushes the universe to be flat in that very early expanding picture. Okay? So how can we tell whether this is true? We have to go out and find out. Is the universe flat or not? We have to measure its contents in some way so that we can find out whether it's flat. So how do you measure curvature? This balloon gives us a clue to how to measure curvature. If you take two lines and you're in a flat space and you send them out, they stay at the same angle from one another forever. That's what you see in this bottom diagram here. All right? In this bottom diagram, you see lines. They just go out at the same angle. That's what you're used to. If instead you have your lines and they're on the surface of something like the Earth, and you send out those lines, they will once again come together at some point. All right? If you send them out from the North Pole, they will come together again at the South Pole. All right? So if you say, what is the distance across between these two lines as a function of distance, it won't be the same as it would be if you look at it in a flat space like this. So by measuring, by setting something out there whose size you really know, and measuring the distance to it, and measuring the angle to it, you can figure out whether the space is curved this way, or curved this way, or straight and flat. It's a geometric measurement. All right? In order to make this geometric measurement in the universe, we need some big triangles. All right? Because we want to measure how the universe, what's its curvature on very large scales. And as we'll see, we're going to look at the biggest triangles that are available and see what they have to say about this flatness of the universe. Okay, so there's a theory, this idea called inflation, and we'll talk about the tests of it in just a few minutes. There's another problem, though, this structure formation problem. Remember, the universe started out very, very uniform, looking like this, all the same everywhere. And now it's very, very lumpy, looking like this. So we have a basic idea for how we think this might have happened, that if there were small excesses in the beginning, a little bit more here, a little bit less there, that those little excesses could grow due to gravity. Gravity pulls everything into those excesses, makes them bigger and bigger and bigger, amplifies the small fluctuations to produce the structure that we see today. That's a hand-wavy picture. We need to turn it into real theory. Now, one nice thing about that inflation theory is that it gives us, as a bonus, a source for those little initial fluctuations. All right, so let me tell you quickly about that. The idea is that if you look on tiny scales at the universe, what you will see is that the universe is filled with these things called quantum fluctuations, little bubbling in the vacuum that changes all the time. What happens with inflation is that those quantum fluctuations, very real things that we can measure things about in the laboratory, those quantum fluctuations get exploded to enormous size and frozen in place. So the little fluctuations we see in the early universe come from this and get expanded out to be big things by the inflationary epoch. Okay? They provide the seeds. The little fluctuations provide the seeds from which the structures we see today form. Now, as I said, we have to have a real theory for structure formation. The hand-wavy model that gravity just pulls things together and makes structures isn't enough. So there's been a long era of simulation of the formation of structure, which says if you start with a certain set of fluctuations in the universe, how would gravity make those fluctuations grow? And there are numerical simulations done now with incredible fidelity, really some of the most advanced computations that are being done, which show us how we would go from the early universe, which is uniform, to the universe we see today. And our job is to compare the universe we see today to what is predicted by these simulations to see whether or not it might be true. OK, so where are we now? We started with this basic Big Bang picture, and we enhanced that picture by adding a theory to explain the evolution of the universe, this general relativity. To that theory, we had to add a couple more elements. First of all, we had to add this idea of inflation to solve the flatness and horizon problems. We added that idea, and it predicted that the universe must, in fact, be flat, that the density must be the critical density. We also added to the picture a story or a theory for the structure formation, which says that there are some initial fluctuations, very small, which grow by gravity to be what we see today. To test these extensions to the basic Big Bang picture, we have to do the following. We have to measure the contents of the universe and its expansion history. Because the contents tell us what the expansion history should be. When we measure it, we find out what it is. We have to measure the flatness of the universe to see whether inflation might be right. And we have to measure the formation and evolution of structure. All of these things require that we look out at the universe and see its whole history and record in as much detail as we can everything that happened. All right? So how do you measure the contents of the universe? How do you figure out how much mass there is in the universe? This is a wonderful subject I can give long talks about because I work on it a lot. But there's basically two ways. You can look at visible objects like the planets and see how much gravity tugs on them. Gravity changes their paths. They don't go in straight lines. They go in circles, and that tells you about how much mass there is pulling in on them. That's Newton's way of measuring mass, still very important in astrophysics. But there's another way. Einstein said that the presence of mass inside something will curve a space-time. So if you measure the space-time curvature, you can measure how much mass there is. All right. Both of those methods are now used very extensively. We look at the motions of objects to determine masses, and we look at the distortions of light that passes through the curved space-time in order to measure the presence of matter. Okay? Both of these methods, since the 1930s, have led to the conclusion that in addition to the stuff we see, all those galaxies and the planets and everything else that we can see, there's a lot more matter there. That's why we went out to measure it, because we wanted to know how much was really there. And what we found is that about 90% of the matter that's in the universe is not glowing, is not making any light. In fact, we have strong evidence that it's not made of the same kind of thing that you and I are. It's something that's called dark matter. The measurements of it are really robust now. We know it's out there. In fact, I wanted to show you one of my own measurements, just to illustrate some of the personal parts of this story. In the late 1990s, we were working on trying to make gravitational lensing measurements around galaxies, because the theory of structure formation predicted that around this little luminous galaxy, the thing that glows, there should be a very big halo of dark matter, a big, large thing around it. So we set out to try and measure that. And what we did was to measure the bending of light as it goes around these galaxies, and to plot that bending of light as a function of distance away from the galaxy. And we did this and published the results for the first time in 2000. And we were able to detect very robustly the presence of dark matter at large scales, far away from the visible matter in the galaxies. That's very difficult to measure without these kind of lensing techniques. So that was one kind of contribution that I made to this process. Now, this kind of measurement, and many other measurements made by many people over decades, led to the conclusion that the total matter density of the universe is not the critical density. It's a lot less. It's about 0.3. Now, observers like myself had been saying this for a decade before the middle of the 90s. Theorists had been not believing it for a decade because they knew it had to be 1. All right? Now, this is a very happy story because everyone was right. All right? I said we had to measure the contents. We also have to measure the history of the expansion. So how do you do that? Greg Tarlay gave some talks about this last year. Basically, what you can do is you can look at certain kinds of exploding stars which have very regular properties. They're called type 1a supernovae. And the distance to those stars can be estimated from the brightness that they have. That distance, as we've seen, tells us how far back in the past we're seeing them. Right? So that tells us a time in the past. And the redshift of those supernovae tell us how much the universe has expanded since that time. So you measure the expansion history. Expansion versus time. You look backward toward the earlier, smaller universe. Now, in just 1998, just 7 years ago, 2 different groups pursuing this kind of measurement came to a really surprising conclusion. The universe is supposed to be slowing down. Its expansion rate was supposed to slow down due to the presence of gravity. In fact, they set out to measure a parameter called the deceleration parameter. They were so sure of the answer that it had a name. Instead, they found out that the universe is actually speeding up. It's actually increasing its rate of expansion. That was a big surprise, the big surprise of that period of time. You can see that represented in the data, and I won't try to describe all the details here, but basically, if the universe had the matter density that we know it has, because we've measured it, then these points should lie along this line. Instead, they lie above the line. All right? And that was the first evidence that there was something other than just this matter density in the universe, something that was making the universe accelerate. All right. The universe contains another component, not just the matter that we know about, but also something else that has a density. We describe that density as omega lambda. And this lambda just might be the cosmological constant that Einstein wrote down in the first place. We don't know yet, but it could well be just that kind of parameter. The current ideas for what this density is focus on kinds of vacuum energy, something that's called dark energy, and that component of the universe, that substance that's in the universe, is driving an accelerated expansion. Now, if you remember back, in the inflationary period, that little bit at the beginning, we had an accelerated expansion. So maybe what's doing this is something related to what did that. All right, so this might not be quite as big a surprise as we might have thought. What you can do is you can try to understand what that component of the universe is and what this component of the universe is. That's the dark energy. This is the matter. And supernova measurements would tell us that it has to be, the combination of them has to be somewhere in this circle, or this little oval. All right? It doesn't tell us where, because they're not good enough measurements yet. They tell us it has to be somewhere in this. If we combine that, though, with our previous measurements of how much matter there is in the universe, what we find is a line that looks like that. That's how much matter is in the universe. This is what the supernovae say must be true. And interestingly, those two numbers came together at a place where the sum of the two of them is equal to 1, the critical density. This inflationary theory said it had to be the critical density. We said it's not matter. And then we discovered there was another component that just made up the difference. Pretty remarkable result. Well worth checking by other means. So how can we check it by another means? We can go check the flatness by drawing triangles. The basic idea of this is a simple one, that if there were fluctuations in the early universe, imagine you start out with a little bit more matter here. That matter is going to push out towards all the stuff that's around it. It's going to create a little ripple, a wave that travels out away from that point. Now, there are lots of these little fluctuations in the early universe. They all send out little ripples. So if you walked in during the rain today and you looked at the puddle, you would have seen many ripples traveling out from places where drops landed. Now, if all those drops had happened to land in the puddle at exactly the same moment, all the ripples would have spread out to the same size. There would be a time scale, a size scale, imprinted on the puddle based on how long ago those drops fell and how fast the little ripples travel outward. That kind of little ripple should be there in the microwave background, because all those fluctuations were there at the beginning. They all propagated outward for the same amount of time in the same kind of material. So there should be a size, sort of a thing we can see in the microwave background that has a fixed size. Furthermore, that size is something we can calculate very precisely. It's very simple to calculate how big those things should be within this kind of picture. And that set distance, the size of the thing sloshing around, sets a ruler out there in space. We predict exactly how long that should be, and now we can go and measure the angle to it and see whether the universe is flat like this, or whether it's open like that, or whether it's closed like that. In each case, we would measure a different angle down here pointing out to this thing that's out there. Completely separate test from the other things that we've talked about. It's illustrated in this picture here from the Wilkinson Microwave Anisotropy Probe website. If the universe is open and we look out there, then what we'll see is the angle is opening out like this, right? So we'll measure small angles to things. The objects will look little in angle on the sky. If the universe is closed, then those lines curve around like this, and we'll see a big angle leading to that thing. And we'll see big bumps on the microwave background, big ripples. If the universe is flat, they should be just right. And just right is about 1 degree in size on the sky. Again, that's a calculation we can do perfectly well without any big input stuff. What was needed to do this was new microwave background data. The stuff that was taken in 1990 by COBE was not good enough. They took pictures of the sky like this that showed there were fluctuations in the microwave background, but they were very blurry. The angular resolution of this COBE satellite was about 10 degrees. And remember, we're looking for dots that are 1 degree across. So instead of seeing the baby universe, they saw this, a really blurry baby universe. And you couldn't tell from COBE data what the answer was. Since that time, however, a new satellite, the WMAP satellite, the Wilkinson Microwave Anisotropy Probe, was launched, and it took images of the early universe that looked like this. Very much more detail, and our baby universe, now you can read the name on the tag. I said we could calculate just what we expect to see, and I want to prove it. Okay? So I went and I looked up a paper from a graduate school colleague of mine, Mark Komiankowski. In this paper, in 1998, he predicted what the microwave background experiments ought to see. Now remember, the theory only says if the contents of the universe are this, then you'll see that. It doesn't tell you what the contents are or anything. So it makes predictions which are different for different contents of the universe. And there's a lot of different things that you can vary. And if we just concentrate on the one we talked about, that total matter density, it predicts how large these fluctuations ought to be on different size scales for different matter densities. And if the universe is flat, you should find things at a certain place, and that corresponds in these figures to 1 degree, just like we saw in the picture. You should find things that are 1 degree in size. And if the universe has a lower matter density, then you'll find things that are actually smaller. This is displayed in a way which is technically different, so that small things are on that side, big things are on that side. So remember, if it's flat, we should see things about 1 degree in size. If it's not flat, we should see things that are bigger in scale like that, if the density is less than that. 5 years later, 2 years ago, the microwave background experiment, WMAP, produced this measurement of that thing that was predicted on the previous slide. So you see this thing? It has a bump, it has another bump, another bump. All those details, there they are. Okay? You can look again, for those of you who work with data, and see that there are error bars on these things that are very small. Okay? This measurement of where this peak is exquisitely made now. And not only the first peak, but the second peak, and even some information about the third peak is included on this figure. This is an enormously important figure because it allows us to measure the size of those objects, and they are 1 degree, just where they were predicted to be. All right? Very precise, very detailed measurements. The prediction, the line that you see drawn on there, is the prediction for a flat universe with omega matter, the amount of matter in the universe being 0.27, and the amount of dark energy or vacuum energy in the universe being 0.73, adding up to a perfectly flat universe. Inflation said it had to be flat. Observers in the early 90s said there's only 0.3 in matter. It turns out there was another component that we found and then proved it was true by measuring the flatness directly, measuring triangles out to the distant universe. So this vacuum energy got confirmed by this. Just like the combined measurements of the supernovae and the matter density, the microwave background came in and told us the universe was flat and pointed to this point in this space, a flat universe that has both matter and dark energy in it. This confirmation just a year or two ago is enormously important because it means that all the pieces hang together. Not just nearly hang together, they hang together precisely. It's really a remarkable thing. So where we are now is we have this basic Big Bang picture, and we have measured the contents and expansion history and the flatness. What's left for us to do is to measure structure formation. This project, the Sloan Digital Sky Survey, measures the structure now in the universe. We go out and measure many, many galaxies. And the idea of this comparison is that if there were lumps of a certain size way back there in the microwave background, and we calculate how big they are, gravity is going to pull everything in one of those lumps in, but the lumps should still be the same size in the universe today. Those were the seeds. They grow into the structures we see today by collapsing inward. We should still have structures of the same size. To see them, we have to look at a lot of the universe. The Sloan survey has been doing this since the mid-1990s, and we're finally able to do it. So if we look at structure on the largest scales, and this is a measure of how likely you are to find a neighboring galaxy around a galaxy. Galaxies are clustered by gravity. It pulls them together. So if you're on a galaxy, you're likely to find another one near it. If you're far away from a galaxy, you're less likely to find another one near it. But there's a special scale, a special size, selected by that microwave background fluctuations, by those microwave background fluctuations, which is imprinted on the structure that we see today. So when we measure this, how clustered are galaxies, we find that there's a particular scale, and that particular scale is exactly where it's supposed to be. All right? That scale is just where we would take those fluctuations from the early universe, run them forward to today. That's where they should be. It's the only deviation we see from this uniform thing. These predictions are the predictions for what you get if there are fluctuations from inflation seeding the structure. If there aren't, it would look like that. So this allows us to check off the third thing in this. And I'll note, this is a paper from late last year. This paper's not 6 months old. It's the first confirmation that the microwave background structure we see really did make the structures we see today. Before that, we had a story, there were fluctuations, maybe they made the structures. Now we have a solid piece of evidence to prove that it's true. This idea of inflation, still rather mysterious, but very powerful, predictive power. It has predictive power that solves the flatness and horizon problems and gives us initial fluctuations to create the structures that we see today. This detailed framework, far beyond the basic three-pillar picture that we had before, keeps being confirmed over and over again. So the final Big Bang scorecard looks like this. There are some basic observational facts, absolutely not in doubt. The universe is expanding today, it's filled with thermal radiation, and it's dominated by light elements. We also have a precisely tested scientific model for explaining it. It explains the expansion history that we see, it gives us the flatness that's required for inflation to be true, and it shows us how structures formed in the universe. All right? This is a spectacular success. This is what we call a fact in science. All right? It's as well proven as anything we know. There are two big mysteries: dark matter and dark energy. Their presence is confirmed in many ways. They're not going to go away. But we don't really know what they are. And much of the work for the coming decade, and perhaps for several decades, is going to be figuring out what those two things are. There are many explanations. I have several theoretical colleagues in the audience here who have many ideas for what these things might be. But they have to propagate those ideas forward in the way that the Big Bang model was propagated forward, to predict things that we can go out and look at in the universe. When they do that, then we might know what dark energy and dark matter are. But until we reach that point where those theories can really be pushed and tested, we won't know. We'll have stories for it, maybe good ones, but we won't have the real tale. What I find so thrilling about working through the last decade is that we seem to have come to the end of finding the basic story for the physical origin of our universe. Over the last 70 years, we got the basic picture, and just over the last 7 years, we had this series of remarkable confirmations, one after the other, all fitting together. It's come to be known as the Concordance Cosmology, because everything agrees so well. There are remarkable mysteries and tons of work for young scientists remaining in this process. But we now know the basic picture. Our universe began in a hot, dense state 13.7 billion years ago, and it's been expanding ever since. That part is established. Some other interesting mysteries remain. And I'll stop there.
Saturday Morning Physics is sponsored by the University of Michigan Department of Physics and by gifts from friends of the program. Local broadcast is made possible by Pfizer Incorporated.